So welcome to Machines 2 Unit 1 session. Myself P.L. Somasundaram from M. Kumarasamy College of Engineering. I am working as assistant professor in the Department of EE. So today we are going to see about the synchronous generators. So in these generators, first session is already handled by one of the professor, Dr. Mr. P.L. Chokalingam. Today I am going to continue the remaining topics from the first unit. So generator, generally everyone knows that the generator means it converts the mechanical energy into the electrical energy. Generally we will give the general definition for the generator like that. So here so the generator is a common terminology. It converts the mechanical energy into electrical energy in the field of electromagnetic field. So why we are saying this as the synchronous generator? So what is the difference between normal generator and this synchronous generator? Normal generator is always converts the mechanical power into electrical power. Synchronous generator means it is nothing but a AC generator. AC generator means it is the alternating current generator. So when the same generator is called as alternator, when it is called as synchronous generator. Alternator means if I am operating a generator, it delivers the power to its own load. So it is called as the alternator. So alternating current generator is called as alternators. When the same alternator is called as synchronous generator. So synchronous generator means if I am connecting n number of alternators in parallel, it can deliver the power to its own load as well as it delivers the power to the common grid also. So all the generators are synchronously operating. So to operate the generators in the synchronous manner, we have some set of conditions. So that will be covered in later. Now he already covered the two topics, construction and the principle of operation. Now I am going to explain you the induced EMF, how it is related with the speed and the number of poles. If it is the synchronous generator, it always runs on synchronous speed. Why? It is required to run the generator at the synchronous speed. Why it is required to run the generator at the synchronous speed? So for that, here we have the definitions. If I have a a generator, it is having two number of poles. It is considered as north pole, it is a south pole. If I am placing a conductor here, this north pole and south pole are not the permanent magnets, these are the electromagnets. These two are the electromagnets. If I am placing a conductor here, once this conductor once the conductor comes across the north pole, the EMF induced in the conductor is in this direction. This like this. The same conductor, by the rotation, if it comes under the south pole, the direction of induced EMF will differ in the conductors. So here I am getting a sine wave. Okay, so it is like a sine wave. So a pair of pole is responsible for creating a single sine waveform. So the number of cycles per revolution. Per revolution, how many number of cycles of EMF is generated here? It is equivalent to the pair of poles. So north and south, it is considered as the pair of poles. So pair of poles is responsible for creating a one number of cycle per revolution. If I am operating this with a the conductor is connected with the prime mover. It is considered as it is the rotor. It is connected with the prime mover. The conductor is keep on rotating. the speed of this conductor is mentioned by N. What is this N? N is the RPM, revolution per minute. N is revolution per minute. But here, if I am converting this into RPS, the number of revolutions per second, then I am dividing this N by 60. By converting the minutes into seconds, I am dividing it by 60. So N by 60. Totally, frequency of induced EMF is going to be calculated here. The frequency of induced EMF is calculated. The frequency of induced EMF is nothing but, frequency is nothing but the number of cycles per second. So here I am going to multiply this number of cycles per revolution is multiplied with the number of revolutions per second. If you multiply these two, these revolutions get cancelled. We will be getting number of cycles per second. We will be getting the number of cycles per second. So the pair of poles is P by 2. Here I am writing that P by 2, it is equal to number of cycles per revolution. Then the number of revolutions per second, it is N by 60. If I am multiplying these two, I will be getting the frequency is equal to P into N by 120. So what is this P? P is nothing but the number of poles. Once if we design the machine, after that we are unable to change the number of poles. Okay, so the P is always constant. What are all the variable parameters in this expression? Synchronous speed and the frequency. So everyone knows that our Indian frequency. So Indian power system is operating at 50 Hz. Our power system is operating at 50 Hz. So 50 Hz is our standard frequency. So to get the 50 Hz, already the number of poles is constant. So I need to keep this speed as constant. So that here the speed is called as synchronous speed. So I can derive the formula for the speed from this. Ns is equal to 120 F by P. From this expression, I can derive the formula for the Ns, 120 F by P. So here, once the poles is fixed after the construction of the alternator, number of poles is fixed. 120 is the numerical value, it is also constant. My speed is directly proportional to frequency, or vice versa, I can write F is directly proportional to Ns. So to maintain the frequency at 50 Hz, I must run my generator at the constant speed. So that I can given the statement here. For a given AC generator, the number of rotor poles is fixed, and then your alternator must run at the synchronous speed to give an desired frequency. So from this we can understand that the induced EMF depends on the number of poles and the speed. So here the speed is the synchronous speed. Okay, so it is the relationship between the induced EMF, number of poles, induced EMF frequency, and the number of poles and the speed. Okay, right. So then we'll go to the next slide. So I already told you that the number of poles, once if we design the winding, the number of poles is constant. After that we cannot change that. So here our generator is having two different types of constructions. But if it is the high power generator, that generator must have a static armature. It must have the static armature and rotating field. So we can write it as a stationary armature and rotating field. So this kind of structure is always used for the high power applications. So the rotating field, if we are using a field, for that we are giving a DC supply. DC supply is required only two terminals, plus and minus. If I am keeping my armature in the stator part, it is a three-phase alternator. I need a three windings. So how do I design the winding for this armature? How do I design the winding for this armature? So here I have explained there are different types of windings. If it is a DC generator or a DC machine, we have only two types of winding. One is called lap winding, another one is called wave winding. Okay, but now it is not a DC generator. Here we are using AC generator. For this AC generator, in the stator we have a number of slots. The number of slots and the number of poles. So these two values must be a even numbers always. We may not have a odd numbers like 1, 3, 5, 7 like that. Both your number of slots and the number of poles should be a even number. If, for example, if I have the 36 slots, so how do I place the winding in these slots? So for that I have different types of winding methodologies. I can choose a single layer winding or double layer winding. It is first category. Second one, I can choose the full pitch winding or short pitch winding. I can choose any one. Then the winding may be a concentrated one or it may be a distributed winding. So these are the three categories. Okay, then what is meant by single layer winding? So before going to this single layer or double layer, for example, if I have the 36 number of slots and I am going to design this generator for 4 pole. So the number of slots is 36, the number of poles is 4. I will be calculating the pole pitch. What is that pole pitch? It is denoted by small n. So the number of slots is 36 divided by the number of poles is 4. 36 divided by 4 is equal to 9. 36 divided by 4 is equal to 9. So what does it means? I already told you that one pair of pole is responsible for creating a single sine wave. If I have 36 slots, I can see the cut section view like this. So it is my slot number 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So I already told you that the number of slots is 36, the number of poles is 4. The pole pitch value is 9. First, I can place the first coil side at slot number 1, where I should keep the next coil side in this 36 slots. So it is the deciding factor. The pole pitch is 9 means 1 plus 9. I need to add with 10th slot. Okay, so the another coil side is kept at slot number 10. Okay, so up to this, up to 1 to 4, 1 to 9, it comes under first north pole. Then 9 to 18 comes under first south pole. Similarly, next 9 slots comes under north pole 2. Next 9 slots comes under south pole 2. So similarly, I can place the conductors like this. If it is the single layer, if I am placing the conductor from 1 to 10, I have only one coil. Each slot is having only one coil side. Each slot is having only one coil side. Okay, that is called as single layer winding. That is called as single layer winding. Single layer winding means first slot to 10th slot, if I am keeping my conductors, each slot is having one coil side. That is called as single layer winding. Next, I will be moving to next one. Yes, one coil side per slot. Yes, here it is a single layer winding. It is my slot. It is called as teeth. It is the conductor. Whatever we have shown here, it is the conductor. One coil side is placed at one slot means it is called as single layer winding. If it is double layer winding, then I will be placing one more coil side in the same slot. I will be placing one more coil side in the same slot. But you just assume that it is my first coil, coil 1. First coil is placed at the slot number 1. You just assume that it is my slot number 1. It is placed at the bottom. Definitely the first coil's next side is placed at the top. Similarly, here it is placed at the top. This second coil's next side comes under the bottom. Similarly, if I am placing two coils in a slot, then it is called as double layer winding. Then it is called as double layer winding. Okay, right. Next, we'll move to the next category. What is our next category? Full pitch or short pitch winding. Yes. Come to here. Come to this. I already told you that if I am having 36 slots, 4 pole, then the pole pitch is 9. Okay, right. As per our first explanation, if my conductor comes under the north pole, it is producing a positive waveform. My next side of the coil, the same conductor comes under the south pole, the induced waveform is in negative. Okay, so I should keep the coil's first side at the north pole, second side at the south pole. First at the north pole, second side at the south pole. So how do I do this? The angle difference between these two, north pole and the south pole, must be 180 degree. If I have only two poles, it is my north pole, it is my south pole. If I am placing the conductor here, these two are creating a one sine wave. So one sine wave means it is creating 360 degree. Okay, one sine wave is responsible for 360 degree. Up to this it is 180. First half cycle, second half cycle covers remaining 180 degree. Totally 360 degrees. Okay, right. Totally 360 degrees. So one pole pitch means it is responsible for 180 degrees. One pole pitch means it is responsible for 180 degrees. So Here the coil's first side is kept at slot number 1, another side is kept at slot number 10. The electrical angle is 180 degree. It is equal to 1 pole pitch. It is equal to N is the pole pitch, 1 pole pitch. If I am placing the conductor like this, it is called as full pitch winding. It is called as full pitch winding. What is meant by short pitch winding? Instead of placing the conductor from first slot to 10th slot or 1 pole pitch apart, or otherwise if it is less than 180 degree, then it is called as short pitch winding, right? So in the compare with the previous slide and this, in the previous slide my conductor's first side, coil's first side is placed at slot number 1, next side is placed at slot number 10. Now it is shorted by one slot reduced by, it is shorted by one slot. Now the next coil side is kept at slot number 9, so it is shorted by 1. Here the pole pitch is not equal to 1 full pole pitch. It is not equal to full pole pitch, or the electrical degree is not exactly 180 degree. It must be less than 180 degree. Then how shall I calculate how much angle it is shorted? So I can calculate the slot angle beta 180 degree by pole pitch. So as per our data, 180 degree by the small n is 9. If you divide these two, you will be getting 20 electrical degrees. So each slot is responsible for 20 electrical degrees. Each slot is responsible for 20 electrical degrees. Here if I am shorted this slot by 20 degree, it means that now the coil is shorted by 20 degree, or the coil span here is 160 degree. Okay, so here it is short pitched by, either we can mention it in terms of slots, one slot, or it is shorted by 20 degree, 20 electrical degrees. Okay, right. It is short pitch. Then by using the full pitch winding and the short pitch winding, I can relate the factor. It is called as pitch factor K suffix P, or coil span factor. So what does it means? If I am connecting a coil in full pitched coil, if I am connecting the same coil in the short pitch manner, if it is the full pitch coil, I can do the arithmetic sum. If it is the short pitch coil, I cannot do the arithmetic sum. It is phasor sum. So by using this formula, I can able to calculate the pitch factor K suffix P, cos alpha by 2. What is this alpha? This alpha is nothing but the angle of short pitch. It is angle of short pitch. Right? Then before going to the next factor, I will explain you about the next one. Third category, concentrated winding or distributed winding. So what is meant by concentrated or distributed? I have already started like this. We have 36 slots. Under each pole I am having 9 slots. Right? So these 9 slots are responsible for one pole. Here I am mentioning it as north pole, first north pole. Here I have 4 poles. So in this 9 slots, I am going to place the coils. But here, now we are discussing about the 3-phase alternator. Okay, so 3-phase means we have 3 set of windings for each phase. So for each phase having one winding, R, Y, B. In this 9, I am going to divide this number of slots per phase. So first 3 slots are representing R phase. In the first 3 slots, we are going to place the R phase windings, or for in other books they will mention it as A phase or first phase. Then next 3, 4, 5, 6, these are comes under Y phase, yellow phase. Then the last 3, this comes under B phase. So now I have divided these slots per phase. So I can write this term as number of slots. First, we are dividing this number of slots per pole. Now I am dividing it to per phase. Okay, now I am dividing it to per phase. It is a numerator, it is a denominator. So, if my number of slots per pole, I already told you that the number of slots is 36, the number of poles is 4, then it is 9. This 9 is nothing but our small n, pole pitch. So I can write this formula like this: pole pitch by the number of phases. It will give small m, or sometimes it is represented like this: SPP, slots per pole per phase, SPP. Okay, so pole pitch by number of phases. As per our parameters, the pole pitch is 9. We are going to design this for as a 3-phase alternator. Divided by 3, I will be having 3 slots per pole per phase. That only made here. North pole. Under the north pole, I have divided it into 3 phases. So first 3 slots contains the R phase winding. Next 3 slots contains the Y phase winding. Last 3 slots contains the B phase winding, or YB. Here I can place the conductors at all the 3 slots, or I can keep it at any one slots. If I am keeping all the slots are filled with the coils, then it is called as the distributed winding. If I am placing a conductor at a particular slot, then it is called as concentrated winding. So if I am keeping the conductors in a particular slot, then I am getting a induced EMF. If I am placing all the conductors in all slots, then it is called as distributed winding. Here also I can generate the induced EMF. So if I am comparing these two, this distributed winding to the concentrated winding, it is related with one factor that is called as distribution factor. So the EMF induced in the distributed winding to the EMF induced if the winding would be a concentrated one. Okay, so I already told you that This M is slots per pole per phase. This beta is the slot angle. Right? If I am substituting in this, I will be getting the distribution factor value, or it is called as breadth factor. Okay, right. So let me move to a simple problems based on this. Okay, right. Like, look at this. First, we have come across the pitch factor. So I have already explained you by using this. I have 36 slots and 4 pole. Find the pitch factor for this. So for the pole pitch, we know the formula, the number of slots by the number of poles. Number of slots is 36, number of poles is 4, we will be getting 9. So the 9 slots are under one pole. These 9 slots are responsible for 180 electrical degree of waveform. Okay, so beta is equal to 180 by 9, I will be getting 20. This beta is nothing but my slot angle. So what does it means? Each slot is responsible for producing a phase difference of 20 degree between the EMF induced in the different conductors. Okay, so it is the pole pitch. It is the, here we are calculating the pole pitch and the slot angle. Next, here they are asking us to find the charging factor or coil span factor. So this charging angle is nothing but short pitch angle. We already know that 180 degree is the full pitch angle value. Now the coil span, as per this data, the coil span is 180 degree. So the difference between these two is 60 degree. So how much is it is shorted? 60 electrical degree. So I can calculate the pitch factor, charging factor or coil span factor. Cos of alpha by 2 is equal to, the alpha value is 60, cos 60 by 2, we will be getting 0.88. It is the pitch factor value. Not only the pitch factor, all the winding factors like pitch factor, distribution factors and the winding factors. All these factor values are always less than 1. Always less than 1 or unity. So we never use this term, always less than 1. Okay, so it is the pitch factor calculation. Next, we already discussed about it. It is a distribution factor. Here we are comparing the EMF induced in the distributed winding to the EMF induced in the concentrated winding. Okay, right. Then now we will calculate the distribution factor. Look at the data given here. Calculate the distribution factor for 36 slots, 4 pole, single layer, 3-phase winding. So you can write the given data as the number of slots 36, the number of poles is 4, the number of phases is 3. Now we are going to calculate the distribution factor. So we are going to find the distribution factor KD. So what is the formula which is required to solve this problem? K suffix D, distribution factor. K means factor, D is the distribution factor. Sine of M, slots per pole per phase, by slot angle divided by 2 whole divided by M into sine beta by 2. Right? First we will solve this problem from the pole pitch. So the number of slots per pole, it is nothing but pole pitch, small n. 36 by 4 is 9. Then the number of slots per pole is nothing but our small n. We are dividing it per phase. So here the number of phases is 3. So 9 divided by 3 is 3. It is our m value. Slots per pole per phase. SPP. Slots per pole per phase. Then the angular displacement between the slots or the slot angle. So beta is equal to 180 degree by n. So 180 by n value is known, it is 9. Here we have already calculated the n value 9. It is 20. So beta is 20. The distribution factor K suffix D is equal to, in this formula I am going to substitute the values, 3 into 20 divided by 2. Here it is 3, beta is 20 divided by 2 whole divided by sin m value is 3, sine of 20 by 2. I will be getting the answer as 0.96. I will be getting the answer as 0.96. So from these two we can come to the conclusion that both the pitch factor and the distribution factor values are always less than 1. Okay. Less than 1. Thank you. Thank you.